This is the most powerful survey telescope in existence. It took 23 countries, 80 companies, 300 institutes, and 3,500 people to build. A telescope unlike any other. It views the sky with a broad, panoramic view, taking in swaths of stars at once, whilst also focusing with the precision of a surgeon, spotting the smallest details from the faintest lights. This is Euclid, and it needs this unique skill set to solve a great cosmic mystery that's baffled cosmologists for more than a century. Because hidden in the darkness of space lies an enigma that influenced the development and eventual destiny of our entire universe. There is a dark universe out there, one we have never seen or detected, but Euclid intends to map it. I'm Alex McColgan, and you're watching Astrum. Join me today in this supercut as we take a look at the Euclid Space Telescope and its efforts to chart the universe's dark matter and energy, and explore the incredible discoveries it has been making along the way. To understand the need for Euclid, we'll first need to start by understanding the mystery that cosmology is facing.
Understanding the structure of this universe is something we only really began to do in the last 100 years or so. We had plenty of understanding of stars before that point, but it was yet to be discovered how far away some of those stars actually were. Scientists before then largely believed that the universe was just a single galaxy filled with stars. Although some astronomers began to spot little fuzzy patches, actually galaxies, in the sky, and postulated them to be island universes external to our own, nothing was proven until the 1920s, when American astronomer Edwin Hubble began studying one such object for himself. While studying what we now call the Andromeda Galaxy in 1923, Hubble realized that one of the stars he was looking at was a Cepheid variable star, a type of star that blinks brighter and dimmer over the course of weeks. Importantly, it had been proven that these stars' periods were linked to their luminosity, so by measuring how regularly the star brightened and dimmed, Hubble could calculate how bright the star should have been. By comparing that to how bright it actually was, he could mathematically calculate how far away it was. Sort of like how knowing that a candle that's further away from you is dimmer than one that's close by. Suddenly, he had a ruler with which he could measure the universe. And what he found surprised him.
The star he was examining was so far away, it had to exist outside our galaxy. Today, we take images of Andromeda and the rest of the cosmos for granted. With a quick internet search, you can find a picture of almost anything out there. But for much of history, this wasn't the case. And to me, it's important to take the time to appreciate these wonders. Since I was young, I've been fascinated by images of the night sky, our sun, planets, moons, and everything beyond. Astrum's videos were inspired by that fascination, which is why I'm excited to share them with you in book form too. Some of you may remember when we released this stunning hardback a few years ago, and now we've decided to bring it back for another limited run. I am so proud of this book. It's a spectacular journey through the solar system, filled with not only the very best images, but explanations that bring our cosmic backyard to life. We have only 700 copies of these, so click the link below or scan the QR code on screen to make sure you get your hands on one before they sell out. For now though, let's look at how Hubble's Andromeda images changed the face of cosmology with the revelation that Andromeda was another galaxy.
This opened up our understanding, but it wasn't long before another surprise arrived. Hubble noticed another strange fact. He was able to see an expanding universe. It felt like an affront, a universe almost like a mobile, dynamic, organic, and expanding entity. It was an observation so disturbing that even Einstein refused to accept it. The German theoretical physicist had just shaken the structures of the scientific foundation by proposing an unimaginable transformation to our old notions about space and time. And even then, he could not accept that the entire universe was something dynamic and changeable. In fact, he was so convinced that our universe was a static entity Einstein set out to modify his original equations by adding an extra element to stabilize the mathematics of the universe. This addition was called the cosmological constant. For Einstein, the idea that the universe was expanding was so distasteful that he initially couldn't bring himself to accept it. And yet, time and Edwin Hubble proved his static model wrong, making a cosmological constant unnecessary. There is an effect known as the Doppler effect that says that the wavelength of radiation stretches if its origin is moving away from you and compresses if it's moving towards you. Because Hubble knew what frequencies the light from these galaxies ought to be arriving at, he could calculate their direction of travel using this Doppler effect. And he discovered that all the galaxies in the universe were moving away from us. It wasn't long before scientists realized that if they were moving away from us now, they must have once been a whole lot closer. The theory of the Big Bang was born. But another strange fact troubled scientists, one that the Big Bang couldn't quite account for. It wasn't just that the galaxies were moving away from us, they were accelerating away from us. The further away from us they were, the faster they were moving. And acceleration requires energy. Where was this energy coming from? Nobody seemed to know, but it seemed to permeate everywhere. To fill this gap in their knowledge, scientists came up with the idea of dark energy. Applying general relativity to this expanding model universe and comparing it to the latest observational data, scientists realized that the particles we could see, known as baryonic matter, made up only 5% of the universe. Somewhere out there is a shortfall of 95%. It was the only thing that made sense. Matter was congregating strangely, as if something invisible with gravity was pulling it closer together. Scientists called this substance dark matter and attributed to it 27% of that mysterious 95% shortfall. But matter was also being pushed apart. The remaining 68% of the universe had to be the energy that was responsible for that. Undetectable, invisible, but everywhere. The maths proved it. There are a few different ideas about the nature of this energy. For starters, Einstein's cosmological constant raised its head again, this time with a new application. Einstein originally came up with the idea of such a constant as a way of perfectly counteracting gravity, a push to balance its pull, to ensure the universe neither expanded and contracted. But if you start with a bigger cosmological constant, you'd get a universe that tipped into constantly accelerating away from itself, just like we see in real life. Einstein hypothesized that empty space might not truly be nothing, but that it held energy, and it could and did create more of itself. This creation of space would create more energy, increasing the pushing power as time went on. It's unclear why space would have this property though. It was more a recognition that it seemed to than an explanation. To fill the gap, quantum mechanics stepped up to the plate. Scientists of this school hypothesized that perhaps virtual particles were to blame for this extra energy. Virtual particles are pairs of atoms that simply pop into existence as a quirk of the quantum wave function that exists everywhere. They don't stick around for long, as they meet and cancel each other out again, but in the moment before their annihilation, they could, conceivably, push against things, exerting force. This theory had some experimental evidence to back it up. There is some suggestion that virtual particles do in fact exist, at least in some form, but when scientists tried to work out how much energy such particles could create, if this was happening in the vacuum of space, their answer proved to be too large. And not just by a little, by about 120 zeros. When your answer is too big by 120 zeros, there's likely something wrong with your maths. Indeed, this answer got the dubious accolade as the worst theoretical prediction in the history of physics. The third main idea is that of a varying cosmological constant. So, not really a constant at all, but rather an adjusting field, like an electrical field or a gravitational field, that accounted for this repelling force throughout space, This force was called quintessence. And it might be the fifth fundamental force of existence if it really does exist. The problem with this idea, however, is the same as the issue with the cosmological constant. There is no explanation as to why it exists. In short, this is still a very poorly understood field of study. More information would be needed before accurate conclusions can be drawn. Spotting something invisible is naturally hard, but studying dark energy through its impact on the universe around us is already underway. Different observatories are attempting this in different ways. BINGO, the Baryon Acoustic Oscillations from the Integrated Neural Gas Observations Telescope in Sao Paulo, Brazil, is a land-based radio telescope that intends to monitor the radiation given off by hydrogen atoms in the dark patches of space between galaxies, to see if there are any unusual distributions of matter that might point to the influence of dark energy. A curious fact about the universe is that matter clusters in waves. It is statistically more likely that there is a distance of around 500 million light-years between any two galaxies than any other number. It's thought that this is to do with ripples in the early universe right after the Big Bang that have coalesced into more solid forms of matter as the universe cooled, locking those ripples into place. Seeing the gaps between such ripples, even in the darkest corners of space, could be very instructive. However, if you really want to spot dark energy's hand over time and space, you need to go big.
And it's for that purpose that ESA launched the Euclid Space Telescope on the 1st of July 2023 from Cape Canaveral, Florida. You need to understand the three things that make this telescope and its pictures so unique. Firstly, Euclid's ultra-wide lens captures more of the sky at once than any telescope ever has. It gathers high-resolution light data from billions of galaxies, some as far away as 10 billion light-years from us. Compared to ground-based surveys, it has 4 times the resolution and 15 times the sensitivity in the near-infrared. It can also spot objects hundreds of times fainter than the ones Gaia can detect. In a single observation, Euclid records vast cosmic structures and precise details of individual galaxies. The result? An image that conveys multiple cosmic scales at the same time, bringing home details in a way that makes researchers giddy. Secondly, Euclid measures subtle distortions in galaxy shapes caused by dark matter's gravitational influence, creating a gravitational lensing map. This is key to understanding how galaxy clusters grow and evolve, while also showing us how dark matter has played a role in literally shaping the universe. And finally, Euclid is creating a 3D map of the universe with 2 advanced instruments. The Visible Imaging System captures ultra-sharp images in visible light to measure galaxy shapes and positions, while the Near-Infrared Spectrometer and Photometer measures redshifts, placing galaxies in 3D space. In short, Euclid is kind of a big deal.
Euclid's mission is to survey a massive patch of sky with a level of detail and sharpness that's 4 times greater than previously achieved by ground-based telescopes. It wants to map everything, going back 10 billion years. The hope is that in so doing, it'll be possible to create a 3D map of the influence of dark energy, with the capacity to see how dark energy's influence has changed or remained constant over all that time. Euclid will also look at individual stars too, but its main objective is sheer volume. This way, the pattern of dark energy will hopefully emerge.
Traveling about 1.5 million kilometers over the course of 4 weeks, Euclid joined its siblings, the Gaia and James Webb telescopes, in orbit around Lagrange Point 2. This location is ideal for studying and imaging deep space. It allows telescopes to keep the Sun, Moon, and Earth behind them at all times so that they never interfere with observations. It's also close enough to Earth that communications are easy. Since L2 keeps pace with Earth's orbit around the Sun, we stay close to our instruments. Euclid immediately started taking its first images, although these photos of starscapes and galaxies were only tests and do not represent the levels of fidelity Euclid was able to manage once it finished its tuning. Once the collaboration process was complete, however, it began its 6-year mission to map out the stars, and hopefully will eventually answer important questions like what is the nature of dark energy and whether our understanding of the laws of gravity is really complete. That was 3 years ago, and it's found a lot since then. So let's take a look. Let's fast forward to October 2024, when ESA's Euclid Space Telescope sent back its first batch of images, as they are some of the best space images I've ever seen. Known as Euclid's First Light, this photo collection is a dazzling tour of the universe's galaxies, and scientists back then immediately started freaking out at what they were seeing. Euclid's photos have called into question our ideas of how the universe evolved, given us new insight into the role of dark matter in structuring the cosmos, and even let us peer into the past by capturing galaxies 10 billion light years away. All in all, the hype in the astronomical community around these images is real, as summed up by one Euclid project scientist. We have never seen astronomical images like this before, containing so much detail. They are even more beautiful and sharp than we could have hoped for, showing us many previously unseen features in well-known areas of the nearby universe. So let me take you on a tour through Euclid's first light images one by one, starting with our map. Thanks to ESA's Gaia and Planck missions, we already had a pretty solid map of our Milky Way. Euclid intended to fill in the blanks. In these first images, it had only covered about 1% of the map it was sent to create, but they are still extraordinary. Between the 25th of March and the 8th of April 2024, Euclid took 260 pictures of the southern sky, covering an area 500 times the size of the full moon we see from Earth. Putting these pictures together, scientists created a mosaic spanning millions of stars and galaxies. And remember, this is just 1% of what it's planning to do. Because Euclid captures both big picture and detailed data at the same time, researchers can see the sky at different scales. From extragalactic views, we can zoom into the galaxy clusters, their core, and even individual galaxies. So let's explore some of these cosmic structures, starting with one of the biggest known in the universe. This is the Perseus Cluster, located 240 million light years from Earth. This image shows over 1,000 Perseus Cluster galaxies and more than 100,000 faraway galaxies in the background. Scientists think the way galaxies are organized can tell us a lot about the distribution of dark matter and dark energy. You see, gravity might cause dark matter to organize itself into filaments. We aren't sure, but NASA scientists believe it's possible that where these filaments intersect, galaxies stick closer together, forming a cluster. The theory goes that if there were no dark matter, galaxies would be distributed evenly throughout the universe, which, as we mentioned, isn't the case. While many galaxies in the Perseus cluster are already known, cosmological simulations predict there should be several dwarf galaxies there too. If we could see those faint galaxies, we could analyze their shape and distortion relative to the cluster and background to determine how dark matter is distributed. The problem is, these dwarf galaxies tend to be overshadowed by older stars shining infrared light, so they've evaded direct observation. Until now. Euclid discovered more than 630 previously unknown dwarf galaxies, which is a huge breakthrough in the study of dark matter. More than dark matter, Euclid is also teaching us about star formation too. Let's go to our next destination and I'll show you. Say hello to irregular galaxy NGC 6822, shining bright 1.6 million light years away. It was first identified as a remote stellar system by Edwin Hubble in 1925. Now, almost 100 years later, Euclid is sending back high-resolution images of the entire galaxy and its surroundings. The James Webb Space Telescope did also image this galaxy a few years ago, but with a much narrower field of view. Scientists are interested in Euclid's wide-angle photos of this galaxy for what they might tell us about star formation and the early universe. You see, stars smash lighter atoms like hydrogen and helium together to produce heavier atoms, including metals. This process happens across a star's lifespan, and is why we don't see many heavier elements in the early universe, because they take time to accumulate. Surprisingly, many of the stars in NGC 6822 have very low levels of metal atoms. By studying low metallicity galaxies like this one, scientists hope to learn more about how galaxies evolved in the early universe. Euclid has made that a monumentally easier task thanks to the color information from his NISP instrument and its wide field of view. Euclid has also revealed several previously unknown globular star clusters and H2 regions in this galaxy. H2 regions are the colorful gas clouds we see here. When stars are born, they emit light so strong and bright that it ionizes the hydrogen gas surrounding them, resulting in these H2 regions. Studying these will help us better understand the cloud properties at the time a star is born, and what conditions are needed for massive star formation. Speaking of globular clusters, here's one in a different part of the sky. Globular cluster NGC 6397 is 7,800 light-years from home, making it the second closest one to us. This image is one part of a wider image from Euclid, which I'll show you in a little bit. Globular clusters are kind of like Hollywood, a high concentration of stars in one place, where everyone is trying to outshine everyone else. What does this mean? The smaller, dimmer stars get drowned out by the bigger, brighter ones. On top of that, they extend quite a long way out from their center, with the radial parts mainly made up of low-mass, faint stars that, until now, have been hard to see. Ironically, it is these faint stars that hold the most scientific interest for unlocking the history of the Milky Way. As David Massadri of the National Institute for Astrophysics in Italy puts it, currently no other telescope than Euclid can observe the entire globular cluster and at the same time distinguish its faint stellar members in the outer regions from other cosmic sources. Hubble actually imaged the center of this cluster in 2021, but to image the entire cluster, including the sprawling outskirts like Euclid did, would have taken it far too much time and resources. On the other hand, Euclid snapped this shot in just 1 hour, and it is absolutely beautiful, both aesthetically and scientifically. Sometimes we see stars arranged like this, and sometimes we see them arranged as spiral galaxies. Yet, despite living in one, we don't actually know how they maintain their shape. The next Euclid pictures aim to help answer those questions. Caldwell 5, also known as the Hidden Galaxy, is hard to observe because it lies in the busy disk of our Milky Way, about 11 million light-years away. It tends to get overshadowed by dust, gas, and other stars. It is considered a look-alike galaxy to our own, which makes it a prime point of interest for researchers. It's pretty hard to study a galaxy you're inside of, since you only get to observe it from one plane. Euclid's near-infrared instrument was able to pierce through the dust and reveal the galaxy in all its glory. We've captured it before from the ground, but with nowhere near the detail Euclid manages. The Euclid image might look normal, as if every telescope can make such an image, but that is not true. What's so special here is that we have a wide view covering the entire galaxy, but we can also zoom in to distinguish individual stars and star clusters. We can trace the history of star formation and better understand how stars formed and evolved over the lifetime of the galaxy, says Euclid Consortium scientist Leslie Hunt. We still don't fully understand how spiral galaxies maintain their structure, or the role dark matter plays in forming them. Euclid's ability to capture this galaxy's sprawling spiral arms and dust lanes in such detail will help scientists understand the link between dust, gas, and star formation on a large scale in a way we've never been able to before. There's one last image I want to show you on this cosmic tour from Euclid's 2024 data, and I've saved you the best for last. Let's see what these colourful clouds are hiding. Our fifth and final photo shows the Horsehead Nebula. It has been photographed by various telescopes before, but never with such a sharp and wide view as Euclid managed. Again, this shot was taken in just 1 hour, which is absolutely mind-blowing. It's like someone just stopped at a viewpoint and snapped the picture. Located approximately 1,375 light years away, this is the nearest massive star-forming region. It lies just south of Alnitak, the easternmost star in Orion's 3-star belt, and is part of the expansive Orion molecular cloud. It is in this swirling nebula that scientists hope to find evidence of many previously unknown Jupiter mass planets. One such planet has already been identified, Sori 62, a young planet 10 times the mass of Jupiter and a temperature of 1,200 degrees Celsius. The clouds behind the Horsehead Nebula are illuminated by UV radiation from nearby star Sigma Orionis, while the clouds of the Horsehead Nebula itself are made up of cold molecular hydrogen, which gives off barely any heat or light. This makes the Horsehead Nebula an interesting place to learn more about star formation, as scientists can observe and compare how stars form in dark versus bright clouds. Sigma Orionis is part of a group of stars called an open cluster, which researchers hope to get a more complete picture of with Euclid's data. For example, free-floating planets have been known to exist in Sigma Orionis, but with Euclid's ultra-high sensitivity, scientists found many smaller FFPs than were previously documented. As one research paper put it, FFPs in that zone appear to be ubiquitous and numerous. This was just the beginning. With another 5.5 years of mission time left, Euclid still had a lot of ground to cover. And by now, I hope you get a sense of the scale and the profound importance of the images it was capturing. But with such scale comes a problem that must be solved. Let me illustrate this point with a story. In September of 2023, Bruno Altieri, an archive scientist working on data from our infamous Euclid telescope, saw something fuzzy in one of the images. Euclid had been busily surveying a huge swath of the sky in an effort to track dark matter and dark energy in galaxies. And what Altieri saw around galaxy NGC 6505 was a perfect, naturally occurring phenomenon for doing just that. Altieri had found an Einstein ring, and when high-resolution images came through, scientists were able to see it in all its glory. Einstein rings are an incredibly rare mirage of the universe. The ring you're seeing in this image is not a truly physical object, but is actually an example of strong gravitational lensing, where the light from a second galaxy hiding behind the first has its light bent towards us thanks to the first galaxy's gravity. Due to the way the gravity from the first galaxy curves space, if the two galaxies are lined up just right, the curvature of light happens equally around all sides of the first galaxy, redirecting perfectly to create the impression of a complete ring. The conditions for this occurring are incredibly rare. If the two galaxies are even a little off, then you will only get an arc rather than a full ring, or you will get nothing at all. But though rare, Einstein rings are extremely useful. Scientists can use them to calculate the mass of everything within the ring, in this case NGC 6505's galactic nucleus, providing them a second tool to detect mass. And if there's more mass detected within the ring than we can physically see, then the difference is likely dark matter. Einstein Rings can also let you see further galaxies than your telescope could normally detect, which can be analysed to learn about the more distant galaxy. There are a lot of benefits, but here's the thing. This discovery, while fortunate, was not how most Einstein Rings will be discovered going forward. The size of the images Euclid is producing is truly daunting. To be clear, the maps being generated are sized in petabytes, hundreds of them. To put that into scale, your computer at home is likely running either gigabytes or maybe up to a handful of terabytes of storage space if it's particularly high end, each terabyte being 1000 gigabytes. But a petabyte is 1000 terabytes. To store some of these star maps properly, you need the storage equivalent of nearly 1000 computers. The data contained in Euclid's maps will be huge.
You remember that 1% of the completed map was released in late 2024?
That segment already contains 100 million sources of light, either stars or entire galaxies. That's just too many for the human mind to handle. There will be thousands of Einstein rings hiding amongst all that data, all those stars, but to find them on our own would take far too long, unless we wanted to take generations in the attempt. It gets worse. Strong gravitational lensing isn't even the main way that Euclid wants to detect dark matter. Instead, it will be looking for examples of weak gravitational lensing. The idea is similar, but instead of a middle galaxy redirecting light, it's an entire galaxy cluster. And instead of a single galaxy behind them having its light bent, it's a number of galaxies that are deviating from the statistical average. You might be asking how on earth that possibly works, but let me explain. There are enough stars and galaxies in the universe that we can predict on average how close together they are likely to be, which means if you look at any particular bunch of stars, you can see if they deviate from that statistical average or not. To detect weak gravitational lensing, you are looking to see if the light sources behind a clump of galaxies are deviating in such a way that the statistical deviation starts to look like a ring. Galaxies appearing where they probably aren't really, because their light is being weakly bent by intervening mass. Good luck spotting that just with your eyeballs. In other respects, weak gravitational lensing works the same as strong gravitational lensing. You can model objects with the resulting ring to detect the presence of invisible dark matter. This high-level calculation is the way Euclid hopes to map much of the dark matter in the third of the night sky it's looking at. Finding examples like this is something you'd never hope to be able to do by the old-fashioned astronomy technique of pointing your home telescope at the sky. The solution? It all comes down to a tool you might have heard of by now: artificial intelligence. AI, specifically machine learning in this case, can be trained to identify examples of weak or strong gravitational lensing in all that data. We have examples where it's already done this, such as when astronomers used AI to identify 56 gravitational lens candidates from images taken by the VLT in Chile. We have further examples where it's been put to good use doing similar tasks. In a citizen science initiative in Japan, 10,000 human volunteers sifted through data from the Subaru telescope, identifying 20,000 galaxies. From this, an AI was trained to identify the pattern and discovered a further 410,000 galaxies in the data with 98% accuracy. Machine learning is an incredible tool in astronomy and has helped find exoplanets in Kepler data, so it can certainly be taught to repeatedly spot Einstein rings or weak gravitational lensing in the Euclid data. Then it's just about having a powerful enough computer or network of computers to run the AI and feed it the petabytes of data and seeing what patterns it detects. This new tool will let us look at the universe in ways we never would have been able to do without it. Even if the accuracy isn't 100%, our understanding will undeniably improve. Who knows what mysteries large patterns like this could solve? Of course, as you may be glad to know, AI is not doing this work alone. There are thousands of scientists who are evaluating the data, guiding the machine learning programs, and verifying the discoveries being made. And in the years between Euclid's first data release and now, a host of other discoveries have been made. In just February of 2026, with the help of Hubble and the Subaru telescopes, Euclid's detection techniques allowed it to uncover something scientists are calling a dark galaxy. A galaxy full of dark matter with very few stars. This galaxy, called CDG2, contains just 4 globular star clusters compared to the Milky Way's 150. These dense collection of stars are reliable indications of a galaxy being present, so scientists know something is there in the darkness. In fact, this is the first galaxy detected only through its globular cluster population. Scientists believe that 99% of the mass present in CDG2 is dark matter. It's incredible to me that there are hidden galaxies floating out there, giving off very little light, and yet being rich in this secret mass. Later in June 2026, Euclid turned its gaze much closer to home, onto the center of our Milky Way. Just take a look at these dazzling stellar images. These images were taken all in the course of just one day, but capture so much detail about our inner galaxy that it is so easy to miss. The sheer number of stars in the center of our galaxy makes it easy for telescopes to be blinded by the sheer amount of light there. Euclid is able to differentiate between the various stars, allowing scientists to get an incredibly clear picture of the stars and planets there, comparable in detail to the Hubble telescope's resolution power, but done in a fraction of the time Hubble would need to take on this. With the image Euclid took here, scientists now have a baseline they will be able to use in detecting future microlensing events as planets move in front of their stars. For instance, when the Roman Space Telescope later looks at this same region and spots a microlensing event, or the moment where the light of a star brightens due to a planet moving in front of it and gravitationally pulling the star's light more towards us, scientists will be able to compare the total mass of the star and planet with the earlier Euclid data of just the star, making the planet's mass and nature easy to calculate. This can offer so much insight into the sorts of planets present within our inner galaxy. But more on all this another time. I actually have a whole video about Euclid's image of the center of the galaxy coming up soon. And finally, Euclid's incredible talent for both widespread yet detailed imaging is proving to be a game changer in the hunt for one elusive primordial object, ancient quasars. The exact nature of the early universe is shrouded in mystery, as the extreme distances involved means light from 13 billion years ago has diffused and is therefore extremely faint to us. It took scientists a decade to spot 10 or so quasars in the first 770 million years of the universe's existence, those that were the brightest and easiest to spot. Euclid has detected 12 more in a single year, plus another 19 relatively closer to home. These 31 quasars in total will offer scientists a better understanding of these colossal, powerful sources of light, which may in turn help us better understand what conditions were like back at the universe's dawn, certainly a period of our history we could do with getting a clearer picture of. This is the power of the Euclid telescope, and there are still 4 years to go on Euclid's mission to map a third of the night sky. 4 more years of incredible discoveries with a telescope that's both big picture and small. Dark matter, strange new galaxies, beautiful stars and nebulae. Euclid will enhance our understanding of it all. Who knows what patterns will emerge from that expansive data? What realizations we will get when we finally hold all the pieces of the puzzle in our hand at once. For now, we will have to make do with what we have. Euclid has so far completed 35% of its star map. There are still so many more discoveries and wonders on the horizon. You can definitely expect to hear more from Euclid in the future. Which of Euclid's discoveries are your favorite so far? What do you hope to see more of in the years ahead? Let me know in the comments below. Thanks for watching. We mention this a lot, but that's only because it genuinely makes a difference. Astrum runs because of people like you who take a moment to join us in what we do. So consider taking 1 minute to look at the Astrum Patreon and see if any of the tiers and rewards interest you. Every member is core to our videos, and you get to watch all of these videos completely ad-free. We truly couldn't make these videos without you. If you enjoy what we do, come join the Astrum community today.